20-1s, welcome back to the world of math videos. This lesson, we are going to look at what's called rationalizing denominators. So we've spent some time adding and subtracting radicals. We've spent some time multiplying and dividing radicals. Well, what rationalizing denominators is when you're looking at radicals, when you have a radical in a denominator, it's just not allowed. It's not considered acceptable. So rationalizing a denominator, if you recall, a rational number is a positive or negative fraction. And a fraction means you have a terminating or a repeating decimal. So that's what a rational is. Well, if I have 2 over root 3, root 3 is not a terminating or repeating decimal. It's an irrational. This is actually an irrational value because root 3 is a decimal that goes on forever. Well, we want to take the denominator and we want to put it into a rational number instead of an irrational. So that's what we're doing, getting rid of roots, radicals from denominators because they're not rational values. It's a process. Some of them are straightforward. Some of them are not straightforward. So if we take a look at page 11, work through a bunch of examples. The examples, we'll do a lot of them in this lesson quickly, but you have to get the process down. So what we want to do is we have 3 over root 2. We don't like root 2. We want to get rid of it. Well, the first thing we're going to do is we are going to multiply the denominator by the radical being eliminated. We want to get rid of a root 2, so we're going to multiply by root 2. This goes back to the multiplying lesson because anytime I have a radical and I multiply it by itself, well, if I show all the steps, multiply the radicands, root 4 is really just 2. Remember, a radical times itself is just the radicand. So if I want to get rid of a root 2, I'm going to multiply by root 2 because root 2 times root 2 is just a 2. All of a sudden, my irrational root 2 in the denominator has now become a 2, which is a rational number. So that's what we need to do. Multiply the denominator by the radical that we're getting rid of. However, with fractions, if I have 1/2 and I want to write an equivalent fraction, well, I could multiply the 2 by 10 to get 20, but I still have to multiply the top by 10 because 10/20 is equal to 1/2. Same thing here. If I'm going to multiply by root 2 in the numerator, I need to multiply by root 2 in my, or if I'm going to multiply by root 2 in the denominator, sorry about that, I need to multiply by root 2 in the numerator to maintain equivalence. Whatever I do to the denominator, I need to do to the numerator. And we end up with 3 root 2. A radical in the numerator is okay. So we now have a value of 3 root 2 over 2. And that is the same as 3 over root 2, but a more acceptable value. You could punch it into a calculator and see 3 divided by root 2 will be the same as 3 root 2 divided by 2. Last thing, well, sorry, I forgot to number that, but the last thing is simplify the radicals as we've been doing all along. Root 2 can't be simplified, so we're good. So that's our process. Next example on this page that we can do is the root of 2/3. Well, remember that root 2/3 we could think of as root 2 divided by root 3. So here's a form. Again, radical in the denominator is not good, so we're going to multiply the denominator by the radical we want to get rid of. Root 3 times root 3 gives us a 3. But to maintain equivalence, I need to multiply by root 3 up top Root 2 times root 3, multiply the radicans, we get root 6. Can we simplify this? Root 6, 6 can't be broken into anything that can root out a power or a factor. So there is the better form because we now have a denominator that is a rational value. That's all there is to it. They get a little bit bigger, but the process doesn't change. 6 root 2 over root 3. Again, want to get rid of root 3 because our radical times itself is just your radicand. Going to multiply by root 3 up top. Well, here, 6 times the coefficient of 1 gives us a 6 root 6. Now, we have to be careful because no, we can't simplify our radicand at all. Root 6 is going to stay as root 6. However, I have coefficients of 6 and 3. If I have a coefficient and a constant, I can reduce those possibly. 6 and 3 can both reduce by 3. So if I reduce by 3 and reduce by 3, I'm left with 2 root 6 over 1. The denominator of 1 does nothing. We can simplify this to just 2 root 6. So make sure that this simplify the radical also means, besides can the radical get smaller, is can you reduce the coefficients and constants? And that's the second part to making sure that it's fully simplified. 4 root 8 over 2 root 5. Now here, we don't like the root 5 portion in the denominator. Some students will multiply by the entire value that's down there. That works. It'll get you the same answer. But really, all we have to multiply by is the root that we're trying, the radical that we need to get rid of. Show a little bit of steps this time just to show you. 2 root 5 times root 5. Well, 2 times the coefficient of 1 is 2. Root 5 times root 5 is just our coefficient of 5. So we end up with 2 for our coefficients times the 5. So we now have a denominator of 10. If you wanted to show more work, just to clarify, 2 root 5 times 1 root 5, 2 root 25, root out the 25, becomes 2 times 5, and there's our 10. So multiply just by the radical you want to get rid of. Multiply by that same radical in the numerator to maintain equivalence, and we get 4 root 40 in this case. So 4 root 40, can we simplify? First, we need to simplify our radical because 40 can be thought of as 4 times 10, so we can root out the 4, which means we're going to go 4 times the 2 because root 4 roots out as a 2. So we get left with 8 root 10 because the 10 is still there as a radicand. 8 root 10 over 10, term up top, term on the bottom. We see that the 8 and 10 can both be reduced by 2. So if I reduce both terms by 2, I'm left with a 4 root 10 over 5. And there's my simplified form. And what's most important about that is that I don't have anything in the denominator other than a rational value. Rationalizing denominators, getting rid of radicals. Well, here's another one. It's the same process, but things just get a little bit bigger, a little bit longer. So again, root 10, don't want it. So we're going to multiply by root 10. So we end up with just a 10 in the denominator. The radical has disappeared. But what we have to be careful of is when we multiply the root 10 to the numerator now, is we have two terms there. Make sure the root 10 multiplies by both those terms. I can't multiply just part of it by root 10. I have to make sure every term gets multiplied by that root 10. So we get left with 2 root 50 plus 4 root 10. And all of that is over 10. Well, we're not finished because we still have that simplify process. Lots going on here. Where can simplifying occur? Well, root 50, we can definitely simplify root 50. Root 10 can't be simplified, so we're just going to end up, right now, we'll keep the 4 root 10, we'll keep the denominator of 10, but 50 could be 25 times 2. So if we root out a 25, we'll be multiplying by a 5 with that coefficient. So we would have 2 times 5, and we would still have the radicand of 2 there. And at that point, with the 10 root 2 plus 4 root 10 over 10, now the second part of that simplifying is, can we reduce? When we reduce, it's no longer like the previous question. If I just go back to that quickly, it's not just a term and a term, reduce the coefficients. Well, this time I now have 2 terms. If I want to reduce, I have to be able to reduce everything. Some students might say, oh, I have a 10 and I have a 10. I could just reduce everything here by 10. Oh, that'll become a 1 and a 1. It doesn't work like that. In this case, we have a 10 and we have a 10, but we also have the 4 we have to deal with. So we have a 10, we have a 4, and we have a 10. The biggest thing that all those terms will reduce by is just a 2. So if I reduce everything by 2, I see that I end up with 5 root 2 plus 2 root 10 over 5. And I have a new radical expression that got rid of the radical that's a root 10 and replaced it or simplified it to a rational whole number 5. There's rationalizing denominators when you have just a single radical in the denominator, a single term. Well, page 12, same kind of process, we just get bigger and a little uglier. So with this one, now we have 2 terms in the denominator, binomial in the denominator. We still have to get rid of this root 6. Now, some of you might say, well, we multiply by root 6. We can't just multiply by a root 6, though, because I would have to multiply both terms by that. And if I multiply both terms by that, well, 3 times root 6 is a 3 root 6. And root 6 times root 6, radical times itself, is just the radicand. Well, I got rid of my root 6, but I added a radical there. So you can't, if you have 2 terms, just multiply by the radical you want to get rid of. It's not that easy. What we have to do is our first step has changed. We don't multiply the denominator by the radical we're trying to get rid of. We multiply the denominator by the conjugate that we have in the denominator. Conjugate from last lesson. What's a conjugate? Well, if you recall, a conjugate is the same information but a different sign. So because we have 3 plus root 6, we want to multiply the denominator by 3 minus root 6. Now, those of you who are on top of this and practiced the last lesson, remember when we multiply conjugates, I just have to square the first values. 3 times 3 is 9. And multiply the second values. Root 6 times root 6 is just 6, but it is a positive times a negative, so it's 9 minus 6. Our new denominator becomes a 3. There's the shortcut when you're multiplying a conjugate. First one square, second one square, and you just have to subtract those afterwards. You get the squared values and you subtract them. Very quickly, to refresh, why does that work? I want you to understand why it works, but it only works with conjugates when we have different signs, positive and negative. Because technically we are doing FOIL here from last class. 3 times 3 is 9. Negative 3 root 6. And then the next multiplying is a positive 3 root 6. And there's the trick. Let's just finish this off. Root 6 times root 6. Radical times itself is just your radicand. But what happened was when we did our multiplying here, 3 times negative root 6, negative 3 root 6, and then 6 times 3 is a positive 3 root 6. Because of the conjugates, our OI in FOIL, the OI's will always cancel out for conjugates. So we're left, whoa, sorry, this should be a negative 6, my bad. Root 6 times negative root 6 is a negative 6. But with that being said, we end up with 9 minus 6, which is our 3. So 2 terms with a radical requires the multiplication of the conjugates. Make sure you are multiplying your numerator by the same value. So we multiplied by the conjugate 3 minus root 6. We need to multiply by the conjugate 3 minus root 6, which leaves us with 6 minus 2 root 6. Can we simplify our root 6? We can't. So we have 6 minus 2 root 6. Can't simplify the radical. However, can we reduce here? Always check to see if we can reduce. We have a 6, a 2, and a 3. There is no common factor. So there's our final value. There's our new radical expression that has no radical in the denominator. Let's try another one. Root 3 over root 5 minus 4. Don't like the radical, so because it's 2 terms, we need to multiply by the conjugate. Same values, but different signs. Again, from what we just talked about, you can do all the FOIL, but you need to become efficient. When you have conjugates, first terms get multiplied. Root 5 times root 5 is 5. The last terms get multiplied. Negative 4 times positive 4 is negative 16. And we end up with a 5 minus 16, which is a negative 11 denominator. No radical, we're happy. Finish it off by making sure whatever you did to the bottom, you do to the numerator. So we multiplied by root 5 plus 4. So we multiply by root 5 plus 4, making sure that we're following distributive property. And we end up with root 15 plus 4 root 3. Root 15 can't be simplified. 4 root 3 can't be simplified. So there's what we can have in terms of radicals at this point. We have an 11, we have a 4, and we have a coefficient of 1. There's nothing that'll divide into those, so I can't reduce. The only thing with this question, really, should never leave a negative in the denominator. we want to move then, or change, I guess you could say, we want to change the negative 11 to positive 11. So this negative, technically you could say, is being multiplied by a negative, because negative times negative is now a positive 11. If I had to multiply by negative 11, I need to multiply by a negative there as well. That negative needs to distribute to both. Negative root 15 minus 4 root 3 over 11. There's the better form because we no longer have the radical. All we did was negative 11 change signs to a positive 11, and if I'm changing the sign here, I need to change my signs up top. Positive became the negative root 15, positive 4 root 3 became negative 4 root 3. That's the quick and easy way to do it. But it all comes down to multiplying by the conjugate. All right, here we go. One more. This one's about as big and ugly as it gets, because now we're dealing with binomial up top, binomial in the bottom. 3 root 2 plus 3 root 3. Two terms, multiply by the conjugate. Gonna have to multiply up here by the conjugate as well. 3 root 2 plus 3 root 3. Now, when you start to get FOIL with radicals, the math isn't tough, but you can lose track of what you're doing. So you need to be careful. Again, because these are conjugates, all we're doing is multiplying the first terms. 3 root 2 times 3 root 2. Well, 3 times 3 is 9. Root 2 times root 2 is just a 2. So we end up with 9 times 2 for that first term. 3 times 3 is 9, and root 2 times root 2 is just 2. So we have 9 times 2, or 18. Multiply the last terms, because the OI, that multiplying outside inner, isn't necessary. Here, we're going to subtract. 3 times 3 is 9. Root 3 times root 3 is just 3, so we get 9 times 3, or a 27. So we have 18 minus 27 there. That's it, which can be simplified, 18 minus 27 to a negative 9. So the conjugates, simplify that. But up top now, we don't have conjugates. We have to do full-on FOIL for everything. So this is going to become a bigger calculation. 3 times 1 is 3. Root 2 times root 2 is 2. So we get the 3 times 1 coefficient. 3 times the 2 is 6. Because that calculation, again, let me show the steps for it. Multiply coefficients. 3 times 1 is 3. Root 2 times root 2 is the 2. Now we go 1 root 2 times 3 root 3, which is 3 root 6. Positive 3 root 6. Now we do root 3 times 3 root 2 becomes a 3 root 6. And now we do root 3 times 3 root 3. Again, 1 times 3 is 3. And root 3 times root 3 is just 3, so we get a 3 times 3. So if I simplify this now, 3 times 2 is 6. 3 root 6 and 3 root 6 is 6 root 6. And 3 times 3 is a 9. So we end up with 6 plus 6 root 6 plus 9. Well, 6 and 9, 15. Plus 6 root 6 over negative 9. Lots of little steps here you have to be aware of. You have to stay organized. And to finish it off then, couple things. 9, 6, and 15 will all reduce by 3, but also we want our negative 9 to become a positive 9. So if I'm going to change the sign in the denominator, I need to change the sign on all the terms in the numerator. And I'm reducing by 3. So my negative 9 becomes a positive 9, but I reduce by 3, so I have positive 3. My new negative 15 becomes a negative 5 because I'm reducing by 3. My negative 6 is reduced by 3, now becomes a negative 2 root 6. And there's the new binomial or radical expression without anything in the denominator in terms of a radical. Negative 2 root 6 minus 5 over 3. There you go. Lots of little steps. But it's all about rationalizing the denominator so there's no radicals in the denominator. There's your assignment, page 290, number 8 to 11, doing A, B, and C in each of these sections, and then 13 and 14. Again, this is just about process. The only way to get good at process is to practice. Have fun with it.